The title of my presentation is Analysis of Musculoskeletal Loading in Lower Extremities for Stilts Work. This work is done together with my colleagues Sharon Chu and Christoph Pan. And my colleagues done experiments, and I run the simulation using anybody software systems. And the stilts are commonly used in construction sites for many tasks, such as tapping and sanding on ceiling or up half of a wall. With stilts, the people can stand half a meter or 1 meter higher off the ground. And compared to other construction tools like ladder or scaffold, stilts has an advantage of mobility and easy to use. If the constructors are well trained with stilts, they can increase the productivity substantially. But it's not clear whether the use of stilts during walking increases the musculoskeletal loading. Intuitively, because you walk on the stilts, you have more loading on foot, and there's a visual and a cyclic impact. The people will have difficulty to keep the posture balance. This is the stilts typically. The right side is typical stilts used in construction site. On the stilts usually constructed with aluminum. The bottom is a foot plate on the contact with the ground. This we put a mark here is used for test. We put a 3 mark on the stilts. With 3 marks, we can determine the location, orientation of stilts during the work. Then the people sit on the foot plate like here. Then here is a several string to hold the foot in place. Then there is the string at the knee side, and this is like a string hold the knee in place. Then with this, the people can walk. There is a mechanism here. You can adjust the height. In this stage is a lower level, about 0.6 meter. This stilts can be extended to a little more than 1 meter if it's needed. It's hypothesized that use of stilts may place workers at increase the risk for knee injuries, or may also increase the likelihood of trips and fall. That seems intuitively because with the stilts work, the people has put more effort, so consequently the leg is easier to get fatigue and is more likely to get a trip and falls. That's why the state of California, under the province of Ontario in Canada, have established legislation against the use of stilts as a preventive measure for occupational safety. But despite these regulations, stilts are still widely used in North America and in Europe in construction side. So the hypothesis of this study is due to the increased height and possibly faster walking speed, the posture stability in stilts walking may be more likely influenced by visual and cyclic perturbations at the work size compared with the normal work. And the stilts had excessive mass moments of inertia to the lower leg. The leg, when people walking, need not only bring the speed for their own body, also the stilts mass to overcome the inertial mass moment of the stilts. The use of stilts in work will increase joint moments on the muscle loadings in lower limbs. This hypothesis seems obvious, but the people never analyzed mechanically and biomechanically how much the stilts will increase the loading in musculoskeletal system of human. So the objective of this study is to develop an inverse dynamic model of stilt work to investigate their effects on the joint movements on the musculoskeletal loading in lower limbs. Especially if with this model you can change a parameter. For example, you change the height of stilts on the mass moment inertia of stilt itself, thereby to look how they influence musculoskeletal loading to help to optimize the design of stilts. Method. The model is developed using antibody system. It's a version 3.0. We have now 4.0, but I personally have never tried. We still use 3.0. So we use the existing three-dimensional gate model, the gate 3D, then modify that existing model to fit our purpose, to include the stilts. The model only include the lower body. That's the two legs on the pelvis, on the upper body, on the influence upper body on the stability is not included. We may do further study to include the whole body. So the model includes hip joints. Hip joints are 3 degrees of freedoms. That's the external internal rotation, abduction and adduction. On the extension and flexion. On the knee joints has only 1 degree of freedom. It includes only extension and flexion. On the ankle joint has 2 degrees of freedoms. That is a plantar dorsiflexion on the inversion, eversion. Each leg contains 35 muscles. There is totally 70 muscles in the whole stilt model. So the key point here is to include stilts. Stilts is very simple. We consider it has only one piece, no joint. Mechanical property of stilts can be determined. They have a mass of 3.6 kilo each for each piece. On the total height of 1 meter about. On the center of mass is 0.4 meter from the bottom, from the ground, if stilts put straight. On the mass moment of inertia in all 3 directions we determine experimentally, also theoretically. I show you how to determine them. If the stilts, you have predetermined the mass center, moment of mass is the C, and the left figure. C is determined. Then you put a string, very thin string, fix the point. Then initially put a small angle. Then the stilts begin to swing around this point. Then use the vibration equation is derived physically. This pedal begins to swing and vibrate. Then it's possible to use swing, for example, 20 times, then you count how much times total, then divide by 20, then is a period. With a period, then you can calculate the eigenfrequency for the pedal. From eigenfrequency, you'll be able to calculate the mass moment inertia around the axis O. Then be very careful. You have to use the shifting equation in the mechanics materials to calculate the mass moment of inertia around the mass center. This is CC. We need to know the ICZ, mass moment around the COM. So in the other direction, this is one direction, the pedal around the axis of the Z. Then you you turn 90 degrees and pedal around the y-axis, do the same job, then you can calculate the mass moment inertia around the z-axis. Then for the x-axis, this along the axis is difficult to directly determine experimentally. Then we estimate it. This is half n r. R is the radius. On the radius is quite you can estimate from the dimension of stilts. Usually this term has a very little value compared to other axes. This is we know during the motion this term is not so significant. So in the test we determined all three mass moment ratio. You can see Cy, Cz are predominant on the two axes. ICX is very small, only 1% of all these. So still 3D meshes we drawn either use SolidWorks, also is possible you scan it directly using a scan machine, then produce a STL file. With this file can be included in the anybody system. So because it's inverse dynamic analysis, we need to do subject tests to walk through and collect the kinematic data. Then in this test, we have 4 healthy construction workers participated in. On the average age are 36 years old, on the 1.8 meter height, on the body mass around 80 kilogram. All subjects are construction work. So they use stilts at least 5 to 10 years. On the subjects worked with or without stilts through a 12-meter straight path. While without stilts, because we want to compare the effects of stilts on the musculoskeletal loading. So without stilts as a basis, then with stilts, we calculate again, then compare the difference and to estimate effects of stilts on musculoskeletal loading. In the test, we test only one elevated height, is 0.6 meter from the ground. There are 18 reflective spherical markers we placed on lower extremities for subjects at anatomical landmarks. That's routinely done by any other locomotion tests. These landmarks are suggested by Van Ham. For the test, with the stilts, 3 additional motion marks were placed on stilts on each side. On the motion kinematics were collected at the frequency of 60 Hertz. Then we use the 2 force platters put on the walkway to collect the ground reaction force at all 3D and also one moment around the vertical axis. The force data were collected at 10 times higher frequencies than the kinematic data. So the key points here in this model is how to include the stilts in the antibody. The stilts is fixed on the foot plate using the any reaction force. Use this function and stilts is fixed on the one point on the plate. Then in the knee side is a stilts connected using a spring, using any force. I will show you how they are connected later. So one key point is that in the normal locomotion model, the force plates will be interacted with the foot. But in stilts work, force plate will interacted with the stilts. So you have to change some mark. Here they show a model with a human model without the stilts, just the data 3D standard in the anybody systems. Second, show the stilts work. Stilts are included in the model and for posture. Then, in order to make our results comparable with those in literature, we analyzed 8 muscle groups in the thoracic, gastrocnemius, Gmax, glutens maximus, and the vastus. Vastus is muscle group, include a couple muscles, and the RF, rector, femur, and the hams also muscle group, and the GM, posterior glutens medians, and the anterior glutens minimus medius, and the 8 muscle groups. And the loading levels of muscle were evaluated by a normalized muscle force. The normalized muscle force was calculated by dividing actual muscle force by the maximal asymmetric force, which is estimated by physiological cross-section area, PCSA, multiplied by muscle strength factor, typically is 35 to 40 Newton centimeters squared. So now I show you the model, how the model is we used. This is a typical model is we just use from Gate 3D Stilts. Then what all these are standard, I will not show. The key point is the motion chart included. There's a small change. You just put several points in Stilts. And this is a major part we put in Stilts. It's like a subroutine in the other software, C software. Then you can see here all Stilts property are input, mass, length, height. Then this sentence shows how to include the picture of the Stilts. This is a 3D mesh of Stilts. We draw fixed one place, and this program included this in. Then this is used to rotate the Stilts to the correct position. Then another point, this is not too much to show. Then I show you the several more important things. This is Stilts. Then other place you have to changing is the environment, the major part. This describes how Stilts interacted with the human body, how the Stilts is included in. There are several points we should pay attention to. First, the force plate foot contact force. This is immediately exists in the 3-gate. We have modified this interactor pressure center with the Stilts, not a foot, human foot anymore. This interaction place is changed. Then other place we have to change it is the interaction with Stilts and the human foot. Yes, is this location. This is the attachment of Stilts to the knee. You can see here we define the stiffness, belt stiffness. Then there is a force, belt stiffness, which is proportional to the position, knee and the Stilts distance. Knee Stilts left is a measurement, which measure the distance. Then for stiffness times the distance is corresponding to a spring. Then another location is the foot, knee interaction. We use, for example, this right foot interaction. We use reaction. Then first you put reaction force. then this linear on the rotational. Use this sentence, then the foot is completely locked on the stilts within 1 point. Other trick in the program is because this anybody system is a bit 3D output, so many muscles, it's difficult to organize the results. Then one trick we do here is we wrote a subroutine output muscle. Then use this program, you can collect all the data. For example, soleil muscle is very simple, only one muscle, is no major change. Gastrocnemius also is only one muscle. But G-max, there's 3 muscles, and we can add here together 3 muscles. And the vastus muscle group, same thing we do here. Then, and so on. Then we define the 8 muscle. All 8 muscle is measured here. Then we also calculate muscle force, on the passive force, active force, all these are calculated. Then finally, this data is I run program, we give a file name, then run this program, all the results is direct output to one single file. Then it's very easy to process the data. So I will not have time to run the program. This is just principle for this. Let's back to the presentation. So the model was driven by motion marks on the ground reaction force we applied as a boundary conditions. And the simulation was run twice because we want to know both joint moments on the muscle force. So in the first run, we calculated the joint moments. In the simulation, we applied the universal muscle on each joint, and the output muscle force is actually joint moment. In the second run, we remove this universal joint muscle and put actual real 3 elements muscle models, and calculate the time history of each muscle. So this is before the test, we have show you because all the data is expressed in the stride period, percentage of stride period. Then from the ground reaction force data, we can calculate the stride period. It's a very simple rule. If you overlap 2 left foot with the right foot, then there is between this there is overlap. Assuming if the human walking in a constant speed, then next time the left foot will start this force over here. Then the stride period is total time minus 1 overlap time. This period, stride period. Then in the overall simulation is calculated in terms of percentage stride period once this is determined. Oops. Yes, this is a joint angle. There is no simulation, not yet. Then we look at the characteristic of Stilts work compared to normal work. This hip external rotation is a positive external, on the negative internal rotation. On the hip flexion in the positive flexion, negative extension. So positive with abduction, negative adduction. Then we look at the hip. Without stilts, the hip, the angle change is larger. You can obvious because the lateral motion without stilts is larger. With stilts is smaller because stilts extend the leg of the human. So the people should walk very carefully and keep the body straight, so make it more stable. Also, the knee joint flexion, you can see, without stilts, the knee has a larger angle compared to with stilts, because extend the leg, the stride distance actually with stilts will be larger because the height increased, the knee don't need to move so much to achieve this. Then the ankle joint, you can see, with stilts, because the foot is constrained, there's no motion theoretically. Without stilts, there's a motion, both elevation and flexion. So this is a ground reaction force with stilts compared to without stilts. X-axis is the direction the human walking. So without stilts, the foot applied more force forward. With stilts, less, because the people have to walk very carefully to prevent the fall. There's less force. Then also the vertical force is normalized to the body weight in this case. Then you see, this without stilts, this valley is deeper compared to the with stilts. This is because the stiffness of stilts foot is harder than the human shoe. Also, because stilts has no sensor, the human walk on the ground, they can sense the touch. That's why there is the more changing on the ground reaction force. Also, external moment is not much. Also, the lateral force is not much. The total compared to this force is very small. This is a joint moment predicted in our model. Hip joint, you can see here, with stilts is a little larger. Hip external rotation is larger than this. On the hip flexion, almost very little change. But one thing for sure, you can look all these hip joint and the knee joint on the ankle eversion on the flexion. Without stilts in the swing phase, the first is force applied force. Then second, the leg just swing if you walk. Then in the second phase, if without stilts, there's no joint moment or very small joint moment. You can see here, because the leg just is a passive motion, just like a pedal. But with stilts, there is still some joint movement. That's because stilts has a moment of inertia. The leg has to overcome the motion of stilts in the swing phase. Even without stilts, it's just the free. With stilts, you have to overcome this motion to stop the stilts motion, actually. That's why there's with stilts, there's a swing in the swing phase. So this is a predicted muscle force. We can look at the major effects of stilt walk is because of swing phase. Because swing phase, gastrocnemius, with stilt walk, you can see here, another peak in the force increase substantially compared to the without stilts. And also, is not all muscle force increased during the stilts walk compared to normal walk. Some muscle increase the force, some muscle is not. We have here 8 muscle. The 5 of these increase the force because of stilts walk. Here, I cannot see clearly. But major thing is the pattern, force pattern is changing here. You can see here is obviously changed. stilts work compared to the without stilts. Also gastrocnemius, RF. So stilts is a change, because of change of the pattern, the posture balance is different. That's why the people have to learn to walk with stilts. Here is a normalized force. Normalized force reflects the efforts the people have to apply during the stilts walk. The maximal normalized force is Solein's gastrocnemius on the RF, on the GMAD also. Then all other are very small. On the train, for both stilts walk without stilts walk, very similar to the actual value comparison. So in summary, use stilts may potentially cause the increase of peak joint moments in the knee extension by approximately 1/4, while you introduce slight reduction in peak joint moments of hip on the ankle. In the 8 muscle group, we analyzed forces in 5 muscle groups were increased, while those in other 3 muscle groups were decreased or almost no change because of stilts. So it's generally this is difficult to predict if stilts will cause injury, but many people may argue even a little increase the muscle force will not increase compared to normal walk, will not introduce injury, because in sports the muscle can increase quite a lot compared to the normal walk. The people does not get injured. The proposed method may provide a useful tool for engineers in their efforts to improve the stilts design, therefore to reduce the musculoskeletal loading on fall risk. So we would like to thank Dr. Frank Busick in National Institute for Occupational Safety and Health and Dr. John Rasmussen on the Sauron Tolan in Anybody Company for their technical support. So the results I presented here is published in Annals of Biomedical Engineering in the recent issue, 2009. If you are interested in more technical detail, you can read that paper. Thank you for your attention. Now, questions.